A jar contains black and white marbles. 2 marbles are chosen without replacement. The probability of selecting a black marble and then a white marble is 0.34. The probability of selecting a black marble on the first draw is 0.47. What is the probability of selecting a white marble on the second draw, given that the first marble drawn was black? The first question I might ask myself is, what are the events in this case? So the events, well, or I guess maybe what the experiments are. So the experiments are, we pick a marble out. The next experiment is we pick another marble out. Okay? Are these two experiments or these two events, are they independent or dependent, first of all? What do we think? Alexandra, what do you think? Independent or dependent? What tips you off that they are dependent events? Yeah, once you see that word without replacement, we know that these are going to be dependent events, because between the first experiment and the second experiment, the marbles that are in the bag have changed. We've taken one out and we haven't put it back in. Okay. Now, which probability are they? So this is going to be a conditional probability question. We know in conditional probability questions that we've got, our formula's got the probability of A and B, the probability of A, and the probability of B given A as our 3 probabilities. Which one of those 3 probabilities are they asking us for? The probability of the intersection, the probability of one event, or the conditional probability of one given the other? Here's where they're actually asking us the question. What is the probability of selecting a white marble on the second draw, given that the first marble is black? When you see this word given, that should tell you right away that this is a conditional probability. Okay? The probability of something given something else is one of the ways of saying, or telling you that the probability that you're talking about is a conditional one. So let's define our 2 events here. What do they tell us? The probability of selecting a black marble and then a white marble is 0.34. So our first event, we'll call it event B. We'll let B be the event where the first marble is black. And it's got to come first because they tell us it's the probability of a black marble and then a white marble. And we'll say W be the event where the second is white, because that's the order we're interested in. First a black marble and then a white marble. So we are interested in finding the probability of selecting a white marble on the second, given that the first marble was black. So the probability of a white one, given the first was black. Okay? Or the probability of event W, given that event B has already occurred. To figure out this probability, we're just going to rearrange our formula for conditional probability. It's going to be the probability of white and black, okay, or the intersection of those two, divided by the probability of B. Okay? We wanted the probability of getting both a white and a black marble, assuming that we've already gotten a black one the first time around. Well, they've given us all the numbers that we need in this question here. The probability of W and B is given to us right here. It tells the probability of selecting a black marble and then a white marble, 0.34. So that's the probability of both events occurring. What about the probability of just B occurring all by itself? Well, the probability of selecting a black marble on the first draw is 0.47. So that's going to be the probability of B. So the probability of W given B is going to be just, well, we just divide those two numbers. 0.72. Punching them into our calculator. Okay. So in this one, you were asked to find the conditional probability. Okay. Let's see which probability we're asked for in the next example here. Robin's friends assure him that if he asks Starfire on a date, there is an 85% chance that she will say yes. If there is a 60% chance that Robin will summon up the courage to ask Starfire out to the dance next week, what is the probability they will go to the dance together? Okay. Now, are these two events, well, what are the two events? What are the two things that have to happen in this problem? Let's let A be the event that Robin asks Starfire out on a date. Okay? And we'll let event B be the event that Starfire says yes. Okay? These are the two things that have to occur in order for them to go to the dance together. Robin has to ask her, Starfire has to say yes. Okay? So what probability are we looking at? Well, we want the probability that they go to the dance together. These are the two things that have to happen for them to go to the dance. So the probability that we're looking for is the probability of A and B. The probability that Robin asks her and Starfire also says yes. Are these two things dependent, these two events dependent? Or are they independent? Well, can Starfire say yes to Robin asking her to the dance if Robin doesn't ask her? No. So one of these things has to occur for the next one to occur. So the chances of her saying yes depends on whether or not he actually asks. So this is a conditional probability question. So we're going to use our conditional probability formula here. The probability of A and B is going to be the probability of A, our first event, times the probability of B given A has already occurred. So our probability of A, the first thing that has to happen, well, the first thing has to happen is that Robin has to ask her. So there is a 60% chance that Robin will actually ask, so 0.60. Next, we want the conditional probability B given A. There is an 85% chance that she will say yes if he asks her, okay? If he asks her, that's the conditional part, okay? So, if there's an 85% chance that if she is asked, she will say yes, we've got both numbers that we need to calculate our probability. So 0.6 times 0.85 gives us 0.51, okay? Or a 51% chance that Robin and Starfire will go to the dance together. Let's look at one more example here, just a little bit more complicated here. A golfer gives herself a 70% chance of breaking par on a calm day, but only a 15% chance on a windy day. The forecast for tomorrow gives a 40% chance of high winds. What is the likelihood she will break par in her round of golf tomorrow? Okay. So what sort of events are we looking at here? Well, they give us some information. One event we're really interested in is her breaking par. Okay. So let's let B be the event she breaks par. what other sort of event are we interested in here? Well, they give us 70%, they give us a percent, they tell us that she's got a 70% chance of breaking par on a calm day, but only 15% chance on a windy day. So whether or not she breaks par depends on whether or not the day is windy or it is calm. So let's define that as our other event. Let W be the event where it is windy. And I'll just put a big comma in between these two let statements. Okay. So what are we told here? 70% chance of breaking par on a calm day, but only 15% chance on a windy day. Okay. Let's think about this in terms of how many ways she can break par. Okay. If it is windy, she has to play really, really well and break par. Okay? She's giving herself that 15% chance on a windy day. She can also break par if it's a calm day. And in fact, it's more and more likely that she's going to break par if it happens to be a day that is not windy. So there are two possible ways that she can break par. Okay? She can break par, let's put it like this, let's put it in terms of probability. The probability of B, okay, of her breaking par is going to be the probability of, let's say, B on a calm day plus the probability of B on a windy day. Because those are sort of the two things that can happen. The next day can be calm, it can be windy. On both days, either calm day or windy day, she has a chance of breaking par. What would the third one be? When it's nice? We'll just say that it's only calm or windy, that these are calm day, windy day. Okay? So you're thinking we need a third event, right? So our third event is the complement of windy. Okay? So we'll call W prime be it is calm. Okay? So there we go. We do have three events, but one of them is just the complement of the other event. Okay? So probability of B on a calm day. Well, these are conditional probabilities, okay? The probability of B occurring here is dependent on whether W occurs or whether W primed occurs. So we want to use our formula for conditional probability for both of these two options here. So probability of B on a calm day is going to be the... So the probability of her breaking par on a calm day is going to be the probability that it is a calm day, or the probability of W complement, okay, that it's not windy, times the probability of her breaking par given that it is not windy, or the probability of B given W prime. The probability of her breaking par on a windy day is the probability it's windy times the probability of her breaking par given that it is windy. So what numbers do we need to pull out of the question in order to put into these formulas? Well, let's see. The forecast for tomorrow gives a 40% chance of high winds. So the probability that it is windy is going to be 40%. What is the probability that it's going to be not windy or calm? That's going to be 60% because those two events are complements. What is the probability that she breaks par given that it's a calm day, or given W complement here? Well, she gives herself a 70% chance of breaking par on a calm day, so that'll be 0.70. What is her probability of breaking par on a windy day? Only 15%, so 0.15. So now we just need to multiply these numbers and add them up. 0.60 times 0.70 is 0.42. So that would be the probability of her breaking par on a calm day. Breaking par tomorrow if, no, the contribution to the probability of her breaking par, factoring in the probability that it's going to be a calm day. Our probability that tomorrow is going to be a windy day and that she is also going to break par is only 0.06. So if we combine those together, there's a 0.48 probability of her breaking par tomorrow is 0.48, or 48%.